Thank you very much. The future depends on what we do today. The future depends on what we do today. The quote is not mine, but Gandhi's. Gandhi's. And I think that it captures beautifully this day 3 of this fantastic conference, and it captures beautifully my next 19 minutes. I'm inviting you into a journey on probably the most disruptive topic on information technology. Trust me, I'm a world traveler. I travel the world. It is my 3rd continent in just 5 weeks, 15 different countries. I'm so keen on traveling that I have made myself a suit made out of passports and visas. I'm not joking. Can you see that? It's made out of passports. Can you check that on camera? I'm so keen, and I learn a lot. I learn a lot on the journey from cybersecurity to cyber resiliency, and especially on disruptive technologies. And quantum computing is one of those very edgy topics that challenges things that we still teach in the university. Challenges things such as creating secret and keeping it secret. Good morning, everyone. My name is Ramsés Gallego. I'm truly blessed of being back to this fantastic city, this fantastic country, this fantastic region of the world where I have friends, colleagues, professionals. I am president of the ISACA Barcelona chapter, former international vice president at the board of directors with ISACA. I'm an ISACA Hall of Fame. And I'm executive vice president of the Quantum World Association. Because I only have 15 minutes left, let me go straight to the core. Quantum computers do exist, period. They do. They are in their infancy. They are babies. But oh boy, they do exist. Actually, what you are seeing on my back is the blueprint of a quantum computer. And there are tricky things in that schematics, meaning there are logical gates and physical gates, and there are switches, and there are light traps. Excuse me? Light traps. Light. In order to operate a quantum computer, you need to stop light. You need to freeze a photon of light in order to operate with it. And as you may imagine, this is not your regular server in your regular data center. They are really difficult. Okay, so let me start with a very basic thing. I know that you know this, but our usual invoices and data and pictures and files and documents, they are made of bits, correct? Bits. And a bit can either have a position of a 0 or a 1. And then the combination of zeros and ones made out our, technology. Okay, for this session, I'm going to call that old computing. Classical computing. Even the fastest computer on the planet works with zeros and ones. The thing is that with quantum computers, they follow the very strange and very edgy laws of quantum mechanics and quantum physics. Quantum mechanics and quantum physics. And there are things that happen in quantum mechanics and quantum physics, trust me, that we humans don't like very much. It's hard for us to understand. And I guess that in something like 10 minutes, I will explain. But this is why I say that quantum computing is not just a revolution. This is why we decided to title this session a Re-Evolution. A Re-Evolution. I am not playing with words, but it builds on decades of IT knowledge. It builds on identity management, access control, classification of data, encryption, tokenization, credential management. Things that we have been doing for decades, but it revolutionizes the speed and computing power. It evolves from things on who has access to what, when and how, for how long. The usual questions that we have been presenting in auditing, monitoring, cybersecurity, cyber resiliency for decades. But the key thing is that speed and computing power, they work differently. Basically, there are 3 states on quantum computing. From your left to your right, you have quantum annealer, analog quantum, and universal quantum. In order to make this entertaining, I'm going to focus on universal quantum, and I only have 16 minutes left. So we are not there yet. I'm going to say it again, just to clarify. I know this is being recorded. We are not there yet. We are right in the middle from quantum annealer and analog quantum. As you may imagine, as we grow from one state to the other, it is more difficult, more expensive, all right? But the applicability and the application of quantum computing as we grow from left to right is greater. Again, we are not there yet in universal quantum, but when we will be in universal quantum, and usually the question I get is, when, Ramsés? Not tomorrow, don't worry. There are a million things that you still need to do in cybersecurity. Million. NIST, DORA, threat intelligence, supply chain, as Uroš was mentioning, and we will talk later in the panel, right? There are a million things that you have to do. But one, understanding that this is coming in 7, 9, 12 years from now. And in my timeline, this is tomorrow or the day after tomorrow. 7 years? 9? Oh boy. Time flies. Time flies. So, for quantum computers to operate, they don't work with bits, they work with qubits. Q from quantum, correct? Listen, this is probably the most important thing I'm going to say in this session. Qubits can either have a position of a 0, a 1, or both things at the same time. This is critical. Both things at the same time. Both things at the same time means that two particles of light, the same particle of light, the same, can be in two different states at the same time. Can be in two different places. Yes, I said that. This is not time traveling, it's a space traveling. I mean it. This has been proved. I'm seeing your faces, by the way, but it has been proved. A photon of light, it's called superposition. 0, 1, or both things at the same time means that that particle can be in a superposition state. This is critical to understand how we can operate with quantum computers. But let me move, because I said, yes, they work. Yes, they work, they exist. Let me tell you something. I really don't think that you will ever, no one in this room will ever acquire, buy, possess, own a quantum computer. I don't think so. But I do think that most of the people here in the room and abroad on camera will use a quantum computer for a number of reasons. The first one, I mean, these things exist. They cost like $15 million. I mean, that's a price tag. But probably you have $50 million. If that's the case, please give me a call. By the way, you have $50 million, give me a call. But you can buy one, yes. But this is not the main reason. For these things, which is not beauty, right? This is part of a quantum computer. I will show you later the CPU, the processor, is right down. Don't worry, I'll have another slide for you. But for this thing to operate, the temperature of the room has to be at 15 millikelvin of temperature. 15 millikelvin. 15 millikelvin of temperature is 180 times cooler than outer space. Excuse me, can you say that again? Yes. 15 millikelvin of temperature, for this to operate, this is very fragile. I'm talking about light, ladies and gentlemen. I'm talking about electromagnetism. This is very weak. It's very fragile. For this to operate, the temperature of the thing has to be at 180 times cooler than outer space. So this is why I don't think that your data center is that cool. So probably yes, but probably no, right? But it's important to understand that this is tricky. In terms of qubits, I said it before. Remember qubits, 0, 1, so both things at the same time? You're following, right? Okay. The world is now at around 2,000 qubit-ish. We don't really know because we have the Googles of the world, the IBMs of the world, that we know where they are. Then we have the Chinas of the world, that we don't know where they are exactly with quantum computing, and they are leading, by the way, big time. Leading, all right? But we are roughly on 2,000-ish qubit. The second part of my presentation will focus on the problems when we get to 10,000 qubits. We are not there yet. I said it before, I'm going to say it again, just to make it clear. They are babies now, but babies grow, and they will become teenagers, and they will become adults. When they will become adults, oh boy, we do have a problem. We are not there yet. So the second part of my presentation, my next 10 minutes, are going to be about 10,000 qubits, okay? In order to do that, I'm from Barcelona, Spain, so let me show you, let me introduce you Mare Nostrum version 4. This used to be the 15th, fastest computer on the planet. Not anymore, but this is a beast. And by the way, it's built on a chapel, just in case you're wondering if the picture is a fake. No, it's not. It's built on a church. So if you ever come to Barcelona, you can go to see the stadium, you know, the Football Club Barcelona stadium and other things. This can be visited. It's a beauty. It's a beast. This thing has 393 terabytes of RAM memory. Oh boy. RAM, yeah. It's massive. Well, guess what? It works with bits, zeros and ones. It's an old computer, and it's a beast. Zeros or ones, bits. You can get roughly the same computing power. Remember, speed and computing power with this thing on my back. This is Google. What is it? This is Google's D-Wave processor. That's a quantum computing processor. There's light in there. It works with light. You trap light. This is the thing that is under that ugly picture that I show you with all of the cables and etc. So at the bottom, this is the thing. And I said it, and I'm going to say it again. You can get roughly the same computing power, the same storage as with Mare Nostrum version 4. I think that changes the name of the game. It changes the name of the game big time. Let me move over a couple of things that I want to show you, because when we get to 10,000 qubits, this is the second most important thing I'm saying this morning. And I'm saying it in terms of geopolitics, cyber warfare, that is coming later into the agenda today. Well, when we get to 10,000 qubits, we are doomed. And we are doomed because any encryption known by humans today, any things that we teach in the university today, Diffie-Hellman, elliptic curve, RSA encryption, things that we teach in class, they're gonna go. Because the moment that we get to 10,000 qubits, we are not there yet, it will mean a world without secrets. And I am not saying this. Actually, there we have official documents, and I think that, Doctor, you're going to love this. This comes from the NSA, the National Security Agency, and the Department of Homeland Security. Basically, it's a recommendation that if these agencies use any of those encryptions, I'm not sure if you in the back can see the following, but if any of your applications, B2B, B2C, customer-facing, are using any of those encryptions, methodologies, and I'm putting money on the table, you do use those encryptions in your developments and engineering. I'm sure of that. Well, they say, should no longer use. Why? Well, Ramsés, do we have quantum computing attacks now? Not that we know of. Remember, we have babies in the house. But they will become teenagers and they will become adults. The moment when we get to 10,000 qubits, magic will happen. Let me open up a parenthesis very rapidly. I only have 7 minutes left. In maths, there are simple problems and complex problems, correct? Simple problems, multiply, adding, that's simple problems. And complex problems, they are called NP problems. NP, complex problems. Like factorizing large prime numbers. Factorizing a large prime number is a complex problem. And we have built the holy disciplines. We in cybersecurity, we the world, we have built the holy disciplines of encryption and tokenization and secret on the impossibility or the high difficulty on factorizing large prime numbers. And there we go. We go with the locks, HTTPS, WhatsApp encryption, endpoint encryption. You know all those things, right? Okay. Then, in 1997, a physicist/engineer called Shor, like Thor, you know, like from the Avengers, but with an S. Shor, S-H-O-R, Shor. He coined the Shor algorithm. The Shor's algorithm basically factorizes large prime numbers. What is the problem of the Shor's algorithm? That we don't have enough computing power today, on Earth, to run it. But when we get to 10,000 qubits, we will. We will. And then factorizing large prime numbers will not be a complex problem anymore. Will be as simple as seconds or minutes. I'm sorry, ladies and gentlemen, that they call it quantum supremacy. I hate it. I hate the word. Supremacy? Come on. There was not another word in the dictionary, but that's how they call it. Supremacy means, sir, that I win, you lose. I destroy you. Supremacy. Actually, it's true that the vendors, IBM, Google, countries like China, they use the word supremacy as something that it was impossible or super difficult to do with an actual computer, including Mare Nostrum from Barcelona. It took like, I don't know, 1,000 years, 1,000,000 of years to do. They can do in minutes. In minutes. In seconds. That's kind of supremacy, I would say. So imagine when we get to 10,000 qubits, I'm going to say it again, not yet. So what in the 4 minutes that I have left, cryptography primitives are safe as long as we can keep, the keys safe, that we can ensure that the encryption and the changes of encryptions are okay, because they are vulnerable to quantum attacks. Let me move, otherwise I'm not going to finish, The new security risks of quantum computing. This article is from 2017. So quantum is not a cool thing now that you guys invited me to speak today on stage, which I'm blessed of course. Thank you for having me today. But this has been going. Again, infancy, teenager, and an adult. Actually, The Economist, coming now, yes. The Economist, which I think is not a magazine being suspicious of being IT related. The Economist is business first, business first, business first. Am I correct? I don't know if you can see it, but it says March 2017. 17. And they dedicated one full magazine of The Economist to quantum computing. Business first, business first, business first. And then the challenges that it represents as an example for finance. But I know that we have government here, we have health, we have different industries. I just took this example. Basically, in English says but not understanding the governance mechanism of quantum computing and the challenges that it represents would be disastrous. Not understanding the challenges that represents a world without secrets, not tomorrow, not next week. Not next quarter. You still have to do DLP, endpoint protection, CASB, cloud governance, access control. You still have to do that, don't get me wrong. But one of those many dimensions should be start thinking what will happen the day after tomorrow, 7, 9 to 12 years. Would be disastrous. And just in case, I'm not only talking about finance here today. Quantum computing talks about healthcare, pharma, research, government, and at the end of the day, any industry in the world that is about creating secret and keeping it as a secret. Actually, my friends at Volkswagen, the car maker, have acquired $15 million. Well, they have the money. $15 million in order to solve this problem. It's an optimization problem. And in 2017, not yesterday, not because it's cool. In 2017, they acquired, one of Google's D-Wave in order to do optimization problem, not one-to-one like the GPS. I know what you're thinking. My GPS can solve that problem, or Waze can solve that problem, and we have different technologies to solve that problem. I'm sorry. No, you're not right. Because the GPS or any of those technologies solve the problem one-to-one. I'm talking about one-to-many. Can I go back to the slide? I'm talking about this problem, hundreds of thousands of, I don't know. I mean, it's impressive in terms of optimization problem, a one-to-many, a complex problem being solved. I only have 1 minute left, but so let me move to things like this one. MasterCard is releasing, quantum computing contactless payment cards. And in order to do for banking or for healthcare, for pharma, for discovery, in order to do Monte Carlo simulations, in order to have portfolios optimization, again, they are in their infancy, but they are growing, and this is absolutely massive. In terms of quantum-resistant attacks, in 30 seconds, I have to let you know that the NIST, National Institute for Standards and Technology in the US, they have released 3 different standards. This is from August this year, so roughly 3 months ago. They have a proposal, and we were talking yesterday about that, remember? So they have a proposal, 3 proposals on post-quantum cryptography. The problem is that there are countries in the world that are not interested in solving the problem. Having said that, you have to like zero ones or both things at the same time. This is again another article for 2017. You have to decide, and this is my question I'm leaving with you today, that quantum computing has not arrived, has now arrived, or both things at the same time. It was a pleasure to present for you this morning. Thank you very much.